So again, you've got periodic trends is the topic for page 45. Objective, like we talked about in objective tracking, is predict relative atomic radius, electronegativity, and ionization energy of elements given their location on the periodic table. So that's our goal. That's our objective that you guys are writing underneath periodic trends. Okay? This first part that we're going to do is going to focus on atomic radius and ion charge. And then on Monday, we'll break that down and go a little bit further, talking about the electronegativity and ionization energy. The first thing we need to talk about here on periodic trends is we need to talk through what's called Coulombic attraction. Okay? Coulombic attraction, which, what do you guys know about the word attraction? Right, so when things come together or go towards something. So Coulombic attraction is how particles with charges are attracted, how they come together, okay, to each other. So Coulomb means charge here, which is why it's called Coulombic attraction, because it's particles with charges that are attracted to each other. Okay, so to kind of break down what Coulombic attraction looks like, what are some things that we know of that would be charged particles that might attract to each other? What are some charged particles that we're thinking about? Right, because protons have what charge? So protons are positive. And electrons are what charge?
Negative.
So then if we're talking about Coulombic attraction in an atom, the thing we're focused on is your protons and electrons, how they're attracted to each other. So with this, kind of how I think about it is if two people are in a relationship, okay? You've got two people that are attracted to each other, they like each other, and their differences are what kind of bring them together. And what makes Coulombic attraction strong with particles, and also what makes them strong in some relationships is going to be similar here. So, for example, if you are able to spend, like if you are pretty close with someone, then you are better able to be attracted with them, right? So if you've got your positive and negative charges that are near each other, that's going to mean that there's more attraction between them, okay? Whereas if you have like a long distance relationship, it can work, right? But a lot of times that's a lot harder because there's more distance between you guys. In the same way, Coulombic attraction is a lot weaker when you have a lot of distance between your two charges. Okay? Questions on how distance affects Coulombic attraction. Okay? So that's the first thing. Closer distance means stronger Coulombic attraction. The next thing, if we've got positive and negative charges, if we've got only one proton trying to pull on only one electron, and then we add an extra proton here. If we're thinking about this now, what do you think's changed about the amount of pull, the amount of attraction those protons have on this electron now? Right. Why? Why is it stronger this time? Right. We've got extra charges here. We've got extra pull from them. So the other thing that affects Coulombic attraction is the number of charges. So you've got closer distance means stronger, and then also more charges with same distance also means stronger attraction. Okay. Questions on Coulombic attraction here? Okay. Then, kind of as a continuation of this, I'm going to really quickly do Bohr models of a couple of elements, okay? So, electron configurations of a couple of elements. So we've got, let's say, Li, Na, and K. Li has how many protons? So it's got 3 protons and 3 electrons then, so 1s2, 2s1. Okay? Sodium has how many protons with it? Awesome, cool. So we've got 11 protons right here. It'll have 1s2, 2s2, 3s2, 3p. Yep, that's 2p6, 3s1. That's better. I knew something was off. Thank you guys for knowing what was off. Then potassium has how many protons?
19.
So I need 19 protons, and then that means 19 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Questions about any of those? All right. Of these, which one has the valence electrons that are the closest to those protons? Which ones have the valence electrons that are going to be closest to the protons?
Okay.
And why do you say K? Okay. Help me circle where the valence electrons are. So Li has valence electrons where?
Second.
Justin? 2s, so that's my valence electron here. All right. And then valence electron for Na is going to be what, Brianna? Awesome. And then for K, I've got what for my valence electron? Aaron?
4.
Awesome. So those are my valence electrons. And so I've got lithium has valence electron in the 2nd energy level. Sodium has valence electron in the 3rd energy level. Potassium has valence electron in the 4th energy level. Which one has the valence electron closest to the protons then?
Li.
Absolutely, yes. It's only 2 energy levels away from those 3 protons. Okay? So then that's going to be the strongest attraction of these elements. It's going to be pulling on those electrons the most. Whereas K, with its electrons way far out in the 4th energy level, still pretty strong attraction, is just a little bit further out. Okay? That's going to play a big role in how our atomic radius is affected here. Okay? And then we'll do two more examples really quickly. We've got still Li, three protons, and we're going to look at N with 7 protons. Li is 1s2, 2s1. N is 1s2, 2s2, 2p3. Okay. Valence electrons for Li are where, Lucas? The 2s. Valence electrons for N are where, Brian? And 2p and what? Oh, so that's the second energy level. What's also the second energy level? Exactly. So both of those are in the second energy level, so both of those are my valence electrons. Okay? Now, if both of these are if both of these are second energy level, then if we drew a Bohr model, is either one further away from the other? Right, they're both second energy level, so there's the same distance, basically. However, what happened to the number of protons that are pulling on them? Right, so I got nitrogen. They're still pulling on just 2 energy levels, but that nitrogen has 4 more protons pulling on them. So which one of these is going to have a higher Coulombic attraction? You guys see why? Okay, so N, nitrogen, is the higher Coulombic attraction. Now, that leads us into talking about the periodic trends and focusing specifically today on atomic radius. So the properties of elements change predictably. You guys already knew this when we went over the periodic table. The ones that we're going to focus on are atomic radius, ion charges, ionization energy, and electronegativity. So we're going to be able to know by the end of today how you move across the periodic table and predict how the atomic radius changes. And then by the end of Monday, do that for atomic radius, ionization energy, and electronegativity. Okay?
What's the last one?
Electronegativity. It's also the last one in the objective, if you needed to know how to spell it.
No.
Okay? Okay, cool. All right, then we already talked about atomic radius a little bit with the launch today. So you guys, who can give me a recap of what we've said for atomic radius? Ian?
Like half of a circle.
Okay, half of a circle, and specifically for atomic radius, we're talking about
Which would be
for what? Atoms. Okay, sorry, I thought I heard X. So then, if you've got Bohr models that we talked about, where would that atomic radius be from, Micah? From the orbits, so like this orbit out here to what? Hmm? I got you. So, if I do a circle, where's my radius? Hmm? I didn't hear what you said.
Radius goes all the way across. Radius all the way across.
That's diameter. So then radius is
Half
half that. So from the, what do we call this thing in the middle here? In the atom, it's called a nucleus. Yes. So from that nucleus out to those outer energy levels. So that's an atomic radius for an atom. So how that's going to change is we're going to look at hydrogen and lithium. Okay? So you guys go ahead and take 1 minute, draw the electron configuration for hydrogen, and draw the electron configuration for lithium. Draw the full electron configuration for hydrogen and for lithium. That shouldn't take you more than 30 seconds. Get that for me in a minute. Increasing your atomic radius.
So would every energy shell be counted as like, so for like 1s, would that be counted like 1 radius? Or would you count like, or would it be a different?
So that's a great question. It isn't that we have like it isn't that each energy level has like a specific number attached to its radius. For what we're doing on periodic trends, we're just thinking relatively. Okay, so first energy level is relatively smaller than second energy level. So it's just relative to each other. It's a really solid question. Okay, so questions on atomic radius as you go down a group. Okay, then again, the reason for this comes down to going down a group means that you have increasing energy levels for those outermost electrons. So for group 1, you go from 1s to 2s to 3s, 4s, 5s, and you can continue going on. That means that as you have a larger energy level, those orbitals extend further and further out. You've got those orbitals being further from that center, the nucleus. Peyton, you had a question? Okay. Okay. Then that leads us into, as you go across a group, this is the situation that we talked about a second ago, where as you go across a group and you've got that Li that's 3 protons, which is 1s2, 2s1, compared to the 7 protons of nitrogen, which is 1s2, 2s2, 2p3. Which one did we say was stronger Coulombic attraction, pulling on the electrons more?
The valence electrons would be closer to the middle of the protons.
Okay, again,
It'd
More.
be nitrogen because there's
More valence
more.
so just to be clear, it isn't that there's more electrons, it is that there's more protons and they're in the same energy level for the electrons. Okay? All of the electrons in that valence shell are all in 2, second energy level, but I've got 4 extra protons pulling them in. So then that means that, can I get a volunteer real quick?
What'd you say?
Can I get a volunteer real quick?
Hey, there you go. What am I doing?
You just come up here. I need someone to show me. Again, decreasing atomic radius as you go to the right because you've got stronger nucleus, okay? So, just a recap, as you move from left to right on periodic table, your atomic radius decreases. If you are looking in a specific period, then those nuclei, which is the plural form of nucleus, those nuclei gain more protons. More protons means it's more positive, which means stronger pull, and the electrons are pulled closer to the atom. Questions on that?
No.
Okay, so then look at your periodic table. Go ahead and get your periodic table pulled out real quick. I want you to silently take 10 seconds based on what we just talked about the size. I want you guys to identify what you think the smallest element on the periodic table is. Okay, I want you to figure out what the smallest atomic radius is based on the trends we just talked about. 10 seconds, go. Based on the trends we just talked about, identifying the smallest atomic radius.
So because this can't fit into here, would it be one of these
It is one of those
for the largest?
for the smallest. Because as it moves this direction, what happens to the radius?
I thought it decreases.
Which means that it gets smaller. The radius gets smaller.
Does that mean hydrogen is the biggest then?
Not the biggest, because also what happens as you go down?
They get small. They get large.
What happens to like the energy levels as you go down?
They increase.
So if I get more and more energy levels, does that make the radius smaller or larger?
So it'd have to be francium.
Eyes on projector, 3, 2, 1. Which do you guys think is the smallest? I'm just going to pull you guys, kind of get a sense of where we're at so far. Which one do we think is the smallest radius? Isabel? Okay, we think hydrogen. Lucas? Helium. Okay, we think what? Abigail?
Francium.
We think francium's the smallest. Okay. One more. Drake, what do you think the smallest is?
I think CI is.
Which one? Okay. So we've got radius increases or decreases going down the periodic table. Increases. It gets more and more energy levels, so it gets bigger and bigger going down. Is that the direction we want to go to find the smallest? We want to go decreasing direction. So then that means that we need to look up. This would be decreasing atomic radius. Then, as I go across the periodic table, do my radius get smaller or larger? Smaller. They get stronger and stronger nucleus, which pulls them in. So then I've got helium is going to be my smallest radius. Okay? Yes? Sorry, Ian, pause for just a moment. Hey, class.
What's up?
You guys